In this lecture, we're going to talk about matched case control studies. And along with that, the actual design, we'll talk about introduction to conditional logistic regression, which can be used to analyze matched case control study data. And we're going to briefly review the laws of probability, which will be necessary in the next lecture for deriving the likelihood function for conditional logistic regression. So matching is one manner in which investigators can control for confounding and bias and also increase precision in studies. Matching consists of pairing or grouping subjects based on pre-specified characteristics. It's also considered a form of stratification that is implemented in the design stage of an experiment. So in a matched case control study, each person with disease who is included in the study as a case is matched with one or more disease-free people who are the controls. And so matching is done based on covariates of interest, often age or ethnicity. And you can also match on residential area or workplace to account for, or other things like that, to account for confounding variables that are not easily measured. A design with M controls per case is known as a 1 to M matched study. And the matched set refers to the case and each of the M controls matched to that case. This is also considered each strata. M is usually between 1 and 5, where 1-to-1 matching is the most common, but you do not have to have the same number of controls for all cases. And you can also have designs where there's more than one case in each set. Here's an example of a matched case control study involving herniated discs and driving. And we're interested in understanding if driving motor vehicles leads to increased risk of lower back pain due to acute herniated lumbar and vertebral discs. And in this case, a 1-to-1 matched design was used. Cases were selected from people aged 20 to 64 in Connecticut who were diagnosed as having herniated discs and had recently acquired symptoms. And controls were sampled from patients admitted to the same hospital as a case with a condition not related to the spine. And they were matched on age. They had to be within 10 years of the case, and sex as well. This resulted in a total of 217 matched pairs. And after an individual was selected for inclusion, data on driving habits and place of residence, which are the exposures of interest, were obtained as well. So how do we model this data? So it's really important to note that if you match by design, at the design stage of your experiment, you cannot analyze your data without taking that matching into account. So if you match by design, so in the design stage of the experiment, you use matched data, then this matching must be taken into account in the analysis stage of your experiment. The probability of disease is assumed to depend on the values of explanatory variables, which may represent exposures of interest and any confounders not used in the matching progress. And the values of matching variables will generally differ between sets, where the matching variables are not included as covariates in the model. So why can't we just use matching variables as covariates, though? Well, there have been a couple of studies that show that this leads to extreme bias in the odds ratio estimates for the covariates of interest. In fact, if you ignore the matching, the odds ratio that you calculate will be a squared version of the true odds ratio. So we really don't want to do this. We're going to get a much higher odds ratio than the truth if we match, or low. Well, higher if it's greater than 1, or lower if it's less. So I'm going to introduce a little bit of notation that will be used here and in the next lecture. So let pk of xik represent the probability that the ith person in the kth matched set has the disease of interest, where k is an index indicating the matched set you're interested in, and I is an index indicating the individual within that set, where you have m plus 1 individuals in the set because you have m controls and assumed to be one case. And here in this notation, we assume that I equals 0 is the case. So pk of x0k is the probability that the case actually has the disease given their set of covariates. And notice that I'm using bold x here. That's because xik is a vector of covariates for the ith person in the case of the match set, where you have, you could write that vector xik1, xik2, all the way up to xikp if you have p covariates. And these xik are not the covariates that we're matched on. Those are implicitly included in the model via the stratification on variable k. These are the other covariates that you'll be interested in studying. So then modeling this probability, the model for this probability is given here, where you take the logit of that probability I introduced with the sum of betas times those covariates and an intercept called alpha k, which is specific to the matched set. Yeah, so notice that each matched set has a different intercept. And this summarizes the effect of the matching variables on the probability of disease, but that the coefficients, the betas, do not depend on that index k. So those do not depend on the actual matching. So the betas, or the log odds ratios for disease, comparing those exposed to covariate B to those unexposed to covariate B, will be the same across all of the different strata or matched sets. So how do we construct a likelihood to find those betas in this setup? Well, by definition, all individuals in a matched set will have the same values for the matching variables. So the probability of selection for inclusion in the study will depend on these matching variables. However, selection probability for the other explanatory variables is assumed to be independent. And we need to construct a conditional likelihood that takes into account the matching done in the analysis. And this is going to be a product of n independent terms, where each of these terms is the conditional probability that the case in a particular matched set is one with a particular observed value for the explanatory variables. And it's conditional on all the values of all the explanatory variables observed in that particular matched set. So how do we construct a likelihood function that allows us to find the estimates for the parameters of interest, beta? Well, first you construct that conditional likelihood for the kth stratum or matched set, and then you combine the likelihoods for all the strata to obtain one giant likelihood across all strata. Where the intuition behind the likelihood in the kth stratum is this is the probability of seeing the observed covariates given the number of subjects in the kth stratum and the number of cases in that stratum. And this setup for modeling the matched case control study is called conditional logistic regression. And we're going to go through this in much more detail in the next lecture, but the logistic model that we will assume the underlying log odds of disease may differ from pair to pair, but the log odds ratio comparing the exposed to the unexposed subject will remain the same across all matched pairs. And this means that the underlying odds of disease can be different from one pair to another. But the effect of the actual predictor, the predictors of interest is the same in all matched pairs. And I'm going to review a couple of the laws of probability because these are going to come up in the next lecture when I derive the likelihood for conditional logistic regression. So take events A and B. The conditional probability, or probability A given B, the notation probability A given B is the conditional probability that event A occurs given that event B occurs. And then probability A and B is the joint probability that events A and B occur together. And then you can relate the conditional probability to the joint probability through this law that I call the law of conditional probability, which is that probability A given B is for the joint probabilities of A and B over the probability of B. And if events A and B are independent, then their joint probability, you can just multiply them together. And we've used this a bunch in deriving the likelihoods. Then there's the law of total probability, which says that if you have a set of mutually exclusive events, which I have B1 up to Bn here, such that the sum of those events is equal to 1, the sum of the probabilities of those events is equal to 1, then by the law of total probability, we have this statement here, that the probability of A is the probability of A given the first part of probability of B times the probability of B all the way up to the probability of A given the nth piece of B times the probability of B. So basically the probability of A is just a sum of conditional probabilities of A given B times the probability of B. Another useful theorem is Bayes' theorem, which states that, which sort of flips the conditional relationship here. States that probability of B given A is equal to probability A given B times probability of B over the probability of A. And we can use the law of total probability from the last side to substitute this probability A in the denominator to get the statement of Bayes' theorem that's put here.